So here we are now, right? This is the Intel Xeon processor 7500 series die. The die is 684 millimeters square. It's about a square inch. 2.3 billion transistors, right? It's roughly 345,000 transistors for each 30 cents that Vannevar Bush mentioned. So we've come a long way. And Moore's law doesn't actually just exist in the domain of silicon and transistors. It also exists in data storage and in communication. So it applies to the number of bits you can keep on a spinning platter or in a flash drive, to the number of bits that you can hold in a fiber of glass or a piece of copper, right? We're seeing the same kind of exponential growth in those places. So and this is the cover of The Economist from March of, I think it's 2010, that basically the world has now collected much more data than it knows what to do with, right? And so it's crying out for some way to attack these massive big data problems that don't just involve automation. So, and I'll illustrate this with another anecdote actually about chess. So Kasparov didn't go away, right? Actually, Kasparov was just arrested in Russia a few weeks ago, which is a whole different story. But this is actually a picture of Kasparov at one of our buildings in Palo Alto playing 12 simultaneous games of chess against Palantir engineers. He won them all, of course, in about 45 minutes. But what happened after Kasparov gets beaten by Deep Blue is that the world kind of needs a new sport. Like before then, it's like, we're going to build a machine that's going to be awesome at chess. It's going to beat the best guy in the world. Then they win. They're like, oh, what do we do now? Right? So they came up with a new sport, and the new sport was freestyle chess, right? And the whole idea behind freestyle chess is there are no rules about how you come up with your moves. You can do anything you want, right? You can like, you know, murder a chicken and swing it around your head and see what the blood spatter patterns. You can read the tea leaves. You can just roll the dice. But more importantly, you can build teams of humans and computers working in concert to come up with the moves. All that matters are the moves that are played. And so there was a really interesting tournament. Kasparov actually wrote about it in the New York Review of Books that happened in 2005, and it was called the PAL CSS tournament. What happened was people didn't actually stop building chess playing computers. They just kept building bigger and better ones and being like, let's see who we can beat. And so there was a group out of, I think, Dubai who built a machine called Hydra. And Hydra is a bunch of networked FPGAs. They just implemented it all in hardware. They're like, it's going to be super fast. It's going to be awesome. Let's have a tournament and show everyone how awesome it is. So they entered their faster than Deep Blue chess playing machine. And also in the tournament are a bunch of grandmasters, like people who are very good at chess. And they're like, well, I'm going to bring my laptop and my favorite chess database. And a bunch of amateurs who are basically there for like the honor of, you know, having their asses handed to them by a grandmaster, right, or a computer. So, but it turns out that the machine, the chess playing computer, gets knocked out of the tournament pretty early by a grandmaster using a laptop, right? And if you think this through, it kind of makes a little bit of sense, right? This hardware implementation of chess is doing nothing but brute force search on the chess space, going as fast as it can to try to figure out what the right move is, but has no intuition about like knocking off different branches and saying, well, you know, there's 30 possible moves here, but actually these are the only two that I would do, right? And the grandmaster can actually do that and say, well, ask the computer, well, of these two, which are the best to do? So the strong human plus a machine knocks the strong machine out of the process. And there's orders of magnitude difference between what Hydra can do and a laptop can do. But the grandmaster using a laptop doesn't win the tournament. The people who win the tournament are two amateurs using 4 different chess programs on 3 laptops, right, or 3 just commodity machines. What they knew how to do is they knew enough about the game of chess to intelligently wire the pieces of software together, and they knew how to use the computer. They knew how to leverage the computer, tell the computer what to do better than the grandmasters did. And just given that little knowledge about chess, their ability to use these incredible machines that we have built let them beat someone who was basically amongst the best in the world at chess in a tournament. Total upset. Everyone was very surprised by this. So if we think about this in sort of notional mathematical terms, we can come up with an equation that looks like this. There's absolutely no rigor to this, so don't hold me to it. But if you want to put my name on it, it's fine. So we have some analytic function composed in terms of C, the computing power, and F, this sort of hidden variable in the system that we're going to call friction, right? We take H to be a constant. That's the human, right, because we're computer scientists. If we're a neuroscientist, maybe we would take that as a variable. But as computer scientists, we'll just say some amortized average of humans. And the idea here is that you're looking at the product between the work of the human and the computer. And there's this hidden variable friction, which is compounding. And the more that you can remove friction from the system, that interface between the human and the computer, the more work you can get the computer to do. And then you're engaging this sort of exponential power of these incredible calculating machines that we've built. If you look at this graphically in like a 3D plot, you can see that varying the power of the human or the computer capability sort of along the bottom gives you these sort of linear changes in the system. But if you actually remove the friction, you get that kind of exponential growth, that sort of show me your hockey stick moment that you're looking for. And there's some examples of this in the real world. So one example that was really fascinating came out of the University of Washington. So one of the problems that people are trying to solve with computers is a problem of protein folding, right? So it goes into everything from disease discovery to designing new drugs to understanding how genomics play a role in our biology. You have to figure out, like, you have these protein molecules and you sort of lay them out and you're like, all right, there's these many hydrogens and these many nitrogens and carbons, but how they fold in 3D actually determines how they interact with other molecules. And there's a bunch of physics around how they fold, and so people just run these sort of brute force searches to say, well, can you fold it this way, and how does it fit in with that thing? So the people at the University of Washington said, what if we turned it into a game? So we're going to use the computer to enforce the physics of how proteins fold, but we're going to build sort of like a video game interface and give it to a bunch of gamers, and they can just sit there and play around with it and see if they can fold the protein, right? And so in 10 separate sort of protein folding puzzles where they matched up computers against the gamification, they came up with, the gamers did just as well as the computer in 3 different puzzles. They outperformed it in 5 cases. And in the remaining 2, they found significantly better solutions than the computer could find alone, right? So this was pretty significant finding. Another example of this that maybe is much easier for people to understand because you've probably used a tool like this is, let's say I ask you to take a picture of someone and write a program to make them look 5 years younger. Anyone who's ever even done any programming in graphics will say, that's kind of hard. And in fact, the way that you would design something like this is probably by simulating Photoshop, right? You would be like, oh, well, this area will apply some blur and we'll do this. And if I'd say, why don't you write me a program that can do this for any photo? A photo that you've never seen, I'm going to give you some random photo, I want you to make this person look 5 years younger. It's basically impossible. It's very, very hard to do. But if you build Photoshop and you put it in the hands of an experienced user, they can do this in about 5 minutes, right? Any photo you give them of a person, boom, 5 minutes, this person looks 5 years younger, right? And so why is this? Think about what Photoshop is doing. The data that goes into Photoshop is a bitmap, right? It's just a bunch of bytes. And everything that Photoshop knows how to do is an algorithmic transformation, the thing that computers are really good at, on this bitmap. The thing that the computer doesn't know is it doesn't know the semantics of the image. It just says, it's a bunch of colors, right, or grayscale. And the semantics only reside in our brain. When we look at the image, we figure out what it is. And so you can think about Photoshop as just being human-guided algorithmic transformations on bitmaps, where the human understands the semantics, and the computer can do the work very, very quickly, right? If you gave someone a list of all the bytes in this image and said, go make them, look younger, here's the algorithm for blur, go ahead and do the math by hand, right? Like it's going to take longer than it would take to write that other program that's going to take forever, right? So, definitely by building these systems where people work in concert, you can actually make a problem that seems intractable by using automation alone seem completely tractable. So that brings us to Palantir. But the place where the Palantir story starts is right here. Well, not here actually in Palo Alto, but at PayPal, right? So here's a picture of the very early team of PayPal, and sort of in the back, the guy with the dark hair and the glasses on the left side, that's Max Levchin. He and I went to school together. I knew him back when they started this idea. It was called Confinity. They were like, all right, here's the idea. You have a Palm Pilot, and someone else has a Palm Pilot. You have a bunch of geeks. They go out to dinner. You need to split up the money. What we're going to do is we're going to beam money between the infrared ports on the Palm Pilots, and you're going to be able to swap sort of encrypted tokens that act as digital cash. Later, when you go back to your computer, you'll plug in your Palm Pilot, you'll hit sync, and then there'll be some sort of program that runs and dials up your modem and tells our servers about what money changed hands, right? This is the original idea of PayPal. I shit you not, right? And then they're like, well, what if, I don't know, what if someone doesn't have a Palm Pilot with an IR port? Or what if, their internet connection isn't working? All right, fine. You can go to the website and put in an email address and you can transfer money back and forth. But that's a backup, right? So as you might imagine, before I get to their pivot, right? So they get their first round of funding, $1 million. They're like, we got to do something awesome because it's the .com era. And so what they do is they hire James Doohan, right? And so for the kids in the audience, James Doohan, he played Scotty in Star Trek. And they got Scotty from Star Trek to beam $1 million from one handheld to another. And that's how they got their funding round. But then they quickly pivoted because everyone's like, yeah, handhelds, whatever. But there was this other company called eBay that was doing these online auctions, and suddenly the ability to move money on the internet made all kinds of sense. Now, the central problem that PayPal ended up having to solve was not how you sort of move money from one account to another, right? The central problem is any time that you're going to move money around, everybody and their brother lines up to figure out how to steal money from you. And so by mid-2000, PayPal was running at something like, they had a 3% fraud rate on 2% margins, which is not a problem you can make up with volume, right? So they said, we got to do something else. And almost out of desperation, they decided to take this human-computer symbiotic approach. So they had some automated tools that could flag things, like yellow flag transactions that look suspicious for one reason or another. But rather than letting those decide whether or not they were fraud, what they would do is they would queue those up, and they had a team of human fraud analysts, like 100 or 200 analysts, I think, that were in like Oklahoma, high school educated analysts they built custom software systems for to basically bring in all the data that PayPal had about the transaction and put it in front of them. And then basically looking at things like where the IP address was coming from and had they seen this credit card number before and all these other questions, they could actually very quickly decide whether or not things were fraud. Now, this ended up being the insight that let PayPal win the payment wars, right? So what happened was, in 2000, if anyone remembers, there was like 11 different online payment companies. eBay even had their own called BidPay. There was one from Wells Fargo. I think Visa was building one. They all went out of business, right? And the reason was, they couldn't solve the fraud problem the same way that PayPal had. And that's why PayPal emerged as the payments leader. And if you're interested, I can go into the reasons why like credit card companies can use data mining to do anomaly detection, but PayPal couldn't. It's actually kind of a really interesting contrast. But I'll leave that for later. So here's Peter Thiel, who is the CEO of PayPal, and realized after the PayPal acquisition at eBay that the central problem they had solved was this one related to fraud, but that the approach that they had hit on was really important. And they could take it and generalize it to build pieces of software that could sort of take this approach to any kind of data problem. And they decided to focus initially on the national security space, just because it seemed like in 2003, post 9/11, it seemed like a good place to begin, and also look at sort of very high-end financial transactions. So basically places where data was their stock and trade, they couldn't afford to fail, and they definitely had budget, right? So what ended up happening was, and this is actually kind of uncharacteristic of Peter, he's actually a founder in the company. He said, we are building this company, not found someone else and invested in it. But he hasn't been involved day to day for long before I joined. He just said, build it, I'm going to own it, here we go. And he's still chairman of the board and sort of involved in that sort of quarterly way. But our overall model, if you go to our website, is to connect the people who care with the data that matters. I've sort of amended it here without friction, because that's really the way that we think about it from a design perspective, is the way that you connect people with data is by removing as much friction as you can from the systems, right? And so at the end of the day, solving very big, complex problems. And the things that I'm talking about here are things like foodborne illness, like doing tracebacks on things like the fungal meningitis outbreak that you're hearing about. Like I don't think we work on that particularly, but at the CDC we work on foodborne illness. Doing things like tracking down missing children in cold cases, looking for patterns of fraud in the stimulus grants, working in actually all kinds of different fraud workflows at commercial banks, and a bunch of other applications in sort of the intelligence and military space. These all have a lot of things in common, which is that they have many different data sources. There's usually an adaptive adversary on the other side that's trying to figure out what you're doing and get around what you're doing. The size of the data is big, and the number of data sources there is quite large. And so what we do is we have built a system that will take data from many different sources, all of which don't agree on how to represent the data. And none of them, most importantly, that represent the data in the way that people actually think about the problem. We map all that into a human conceptual ontology, right? So if you take a researcher at the CDC and say, I have all the data here on foodborne illness, it's in one big Oracle database. Here's a SQL prompt. They go, I don't know what to do with that, right? I know everything that you could ever ask about E. coli, but I really don't know how to do a left outer join.